Hello students, today we will discuss about conduction in solids. So let us consider a semiconductor material, and you know there are some very few conduction electrons or free electrons in the conduction band due to the thermal energy or temperature of the material. And while you have very few holes in the valence band, and when we keep such a material with a potential, when you apply it is connected to an external potential, what will happen? Yeah, it will get the energy, further energy. So the electrons in the conduction band will move towards the positive potential of the cell. So that is called the conduction due to electrons, free electrons. While the electrons, some electrons are bonded inside the atoms in the valence band. So what will happen to those electrons? They will get sufficient energy from the external applied voltage, and then correspondingly they will overcome the forbidden energy gap and become free electrons. So they will fill up the conduction band. So what will happen to the bond in the atom? What will happen in the bond? Yeah, since the electrons are freed from the valence shell of the atom, what will happen? You can see those freeing of electron from the valence band will generate a hole. What is a hole? Hole is vacancy of electron in the bonds. Okay, so there are two kinds of material conductions in solid. One could be due to free electrons, another could be due to the holes. While the holes are in valence band and the electrons are in conduction band, and since they are already free, these free electrons require very less energy for further flow, so they will have greater mobility than holes. While in the case of holes, holes are in valence band, and the electrons in the adjacent atom can fill the holes. So what is a hole? Hole is a vacancy of electron in the bond. So another electron in the another atom can come to the hole and fill it up, and consequently a hole is made in the neighboring atom. That is how an electron is moving. Not the electron, hole is moving from one point to another. That means if I have an atom like this, if one electron is made free, then what will happen? A hole is created, and the electron in another electron in the neighboring atom can fill up this hole. So in the process, what will happen? This electron, there is a vacancy of electron, and that will contribute a hole, while this hole will be filled up and it becomes a electron filled. So there is a generation of hole in the neighboring atom. So that is how an hole is moving from one atom to another, or in turn, in fact, it is the electron moving from one atom to another. Okay, so these electrons are not moving from, not passing from valence band to conduction band, but the movement is only inside the valence band itself. That is why the holes are hole will be having a greater attachment to the nucleus, or to the lattice, and hence they have less mobility. So the free electrons are mostly present in conductors, while in semiconductor the conduction can be due to both electrons as well as holes. So now coming back to semiconductors, we will study more about semiconductor. There are two different types of semiconductor. One is called intrinsic semiconductor, another is called extrinsic semiconductor. So in an intrinsic semiconductor, it is called pure form of semiconductor. For example, pure form of germanium, pure form of silicon. Those are tetravalent atoms. And what do you mean by tetravalent atom? That is, it will have 4 electron in its valence shell. All other inner shells will be filled up, while there will be 4 electrons will be there in the valence shell or the outermost shell. So, and you know, for an atom to be stable, the outermost shell has to be filled up with 8 electrons. So that is not possible here. So what will happen? It will make bonds with, so this is the nucleus of the atom. For example, I can write it as silicon. Okay, so silicon is having 4 electrons. So what will it do? It will pair up or share the electrons with the neighboring silicon atom. So what will happen? So a bond formation is formed, and similarly it will share up with another electron of another atom, neighboring atom, and a bond formation is formed, and similarly all the 4 electrons will be shared with neighboring atoms, and correspondingly you will be getting 8 electrons as a total. That means the system will become stable. Okay, so to complete the octet, it will share the electrons with the neighboring silicon atom. This is how a stable structure is formed. And energy gap in the case of germanium is only 0.72 electron volt, while in the case of silicon it is 1 electron volt. So it is small, it is a very small energy gap, and what happens is that at room temperature or ordinary temperature is sufficient to give energy to the electrons in the atom, and these atoms will be made free. Okay, so when they become free electrons, they will occupy the conduction band, and because it has become free, you can see there is a vacancy of what? Hole. Vacancy of electron in the bond. So that vacancy of electron is what you term as holes. So due to the temperature, as one electron is freed from such a pure semiconductor, it will produce a hole. So there is equal production of electrons and holes due to the temperature. So those charges are called intrinsic charge carriers. And what is the speciality of intrinsic charge carriers? The number of conduction electron will be same as the number of holes that is created. Okay, so what will happen to the Fermi level? Fermi level is the center of gravity of charges. So you can see that in the conduction band there are lots of electrons, and in the valence band there are equal number of holes. So there are equal number of holes and equal number of electrons in the conduction band. So what will be the center of gravity? Center of gravity will occupy the center of the forbidden energy gap. So this is where the Fermi level would occur in a intrinsic semiconductor. The Fermi level will occupy the center of the difference between conduction band and valence band. So now coming back to the extrinsic semiconductor, extrinsic means they are doped with some impurities. So they could be of two types. You can dope it with a pentavalent atom or a donor atom. So in that case there is an extra electron contributed by the donor atom, and hence the name N-type semiconductors. And other is acceptor atom. That means we are doping it with a trivalent atom. So there is a less number of atoms involved in forming bond formation. So correspondingly they are called acceptors, and hence a p-type semiconductor is created. Okay, so there are two kinds of extrinsic semiconductor, p-type and n-type, based on what is the dopant that is added. If it is pentavalent, there is an extra electron, and hence n-type. If it is a trivalent atom, there is a vacancy of electron, and hence holes are created, or p-type semiconductors. So let us see it in detail. So for n-type semiconductor, the material, the dopant, are pentavalent atoms like phosphorus, antimony and all. So here I have shown a phosphorus atom. So phosphorus atom, so let us consider this one and this one 2, 3, 4 and 5 at 5 electrons are there in the valence shell of the phosphorus. So it will form those electrons can pair up or share with the silicon atom. So it will take part in bond formation with the neighboring atom. So there is an extra electron which is not taking part in bond formation. So that is very loosely bound to the atom. So that electron can be easily made conducting or free with the application of electric field or a temperature. So if sufficient temperature is given or if sufficient electric field is applied, you can excite that loosely bound electron of the phosphorus and make it free. So each dopant atom will contribute one conduction electron without creating hole. Why no holes is created? Because it is not present in the bond formation. Only if there any vacancy of electron in the bond, you can term it as a hole. There is no vacancy of electron in the bond. It is just loosely bound to the phosphorus. So it will contribute a conduction electron, but no holes are created. So what is a inference from that? Negative charge carriers are created and hence the name n-type semiconductor is given to such kind of extrinsic semiconductor. So the donor atom, what will happen to the donor atom? It is losing one electron. So if it lose one electron and negative charge is going off, so what will happen to the neutral form of phosphorus atom? It will become positive. So it become positively charged ion. But can it take part in conduction? It is also a charged ion, right? No, it won't be taking part in conduction because it is fixed to the lattice due to the bond formation with other neighboring atom. So it is in a pure semiconductor we have seen that number of electrons created due to temperature is same as the number of holes created. But in the case of n-type semiconductor, since each dopant atom contribute one conduction electron, the number of electrons will be more than the number of holes. How the holes are created? Holes are there already due to the intrinsic temperature of the material. So in addition to that, so there will be equal number of electrons also, but in addition to that, the dopant also contribute one electron each. So the majority charge carriers in n-type semiconductors will be what? Electrons. So what will happen to the Fermi level? Fermi level will shift towards the conduction band. Why? Because the conduction band has more number of electrons than holes in valence band. So what will be the minority carriers? They will be holes. Since the majority carriers are negatively charged electrons, the name is given as n-type semiconductor. Similarly, p-type semiconductors can also be explained. So in that case, we have a trivalent impurity that is added. It is called acceptor atom, and we'll see why it is called acceptor, because it has 3 electrons in its valence shell. So 3 of them will take part in bond formation with the neighboring silicon. So the one neighboring silicon doesn't have a electron to complete its bond formation. So there is a vacancy of electron in the bond, and that vacancy is called hole. Okay, and the electron from adjacent silicon atom can come to fill up this hole. So what will happen? In turn, it will produce a hole here. Okay, so since this hole can accept electrons, this atom or dopant atom is called acceptor atom. Okay, so in the case of p-type semiconductor, one bond is incomplete, and that is called hole, or that will enable conduction in valence band. So since there are positively charged carriers, they are said to be p-type semiconductors. So what will happen to the acceptor atom? Because it is having one that is positive charge will be given to the, or will be moving about it will lose positive charge. So what will happen to the accepted atom? Accepted atom will become negatively charged. But they cannot take part in conduction because it is firmly fixed to the lattice. Why? Because they are bonded with the neighboring silicon atom. So it cannot move along. So as mentioned earlier, in a pure semiconductor, there would be equal number of electrons and equal number of holes, which is called intrinsic charge carriers, which are formed due to temperature. But now by doping with trivalent atom, you have more number of holes. So the majority charge carriers in p-type semiconductor will be holes, while in the electrons will be the minority carriers. So hence the name, because positively charged carriers are the majority, the name is given as p-type. So in that way we can remember the name of the semiconductor. So what will happen to the Fermi level? Now the more charge carriers are in the valence band. So the Fermi level, or the center of gravity of charges, will be closer to the valence band. Okay, so just a conclusion of what we have discussed. So semiconductors have been discussed as intrinsic, it could be intrinsic or extrinsic as p-type and n-type. So in intrinsic, it was equal number of electrons and holes, while in p-type the holes are the majority, and in n-type electrons are the majority. So if you check the Fermi level, that is band diagram, energy band diagram, in intrinsic semiconductor, because there are equal number of electrons in conduction band and equal number of holes in valence band, the center of gravity or the Fermi level will lie at the center of the forbidden band gap. But in the case of p-type, there are holes, more holes towards the valence band. So the Fermi level will shift from the middle position, it will shift towards the valence band. It will be lying closer to the valence band. While in the case of n-type, there are more electrons in the conduction band. So the center of gravity will be closer to the conduction band, or the Fermi level will be closer to the conduction band. And in terms of charge conduction, you can see that in the case of p-type, the majority charge carriers are holes. So here you can see there are white circles, which indicates more number of holes and very few number of electrons. So when you give a potential, when you connect a such a semiconductor to the battery, what will happen? Due to the positive charge, what will happen? The holes will be repelled by the positive charge, and it will move towards the other side of the material, while the electrons are attracted by the positive charge. Okay, so the holes will be continuing. Holes direction is given by like this, and the electron direction will be opposite to that. So the major flow is due to the holes. Okay, so here also it must be holes. It must be, the orange line shows those are the conduction of holes. Okay. And in the case of n-type semiconductors, electrons are the majority. So you can see the yellow color represents the electrons. So there are more number of electrons, and when you attach to the battery, the electrons will be attracted towards the positive side of the battery. So here you can see there is flow of electrons, and while the holes are repelled by the positive side, so it will come up to the negative side. Okay, so this is how you explain the current conduction in extrinsic semiconductor, in p-type and n-type conductor. So we'll see later about p-n type of materials, which is called p-n diode, in our next section. Thank you.